So here's a quick refresher on young stars and SEDs. So when we do this live and in person, I'm going to do another one of these break us up into groups thing, where you get to think about what you know about this diagram. And we have data from very many places. Where do all of the wavelengths of light originate? And so we'll talk about this a little bit. So to highlight this, because I think this may be the part that you might be looking at this recording to find, this is a simple sketch, not to scale, of a young star. So you've got the young, fully convective star in the middle. Because it is young and fully convective, it is rotating quickly, and so it has gigantic star spots. Those big star spots make X-rays and ginormous flares. The circumstellar disk circles the star, but because the star is young and fully convective, it has a strong magnetic field. That's what stellar B means. And 2 kilogauss is a lot. Our sun is very much weaker than that because our sun is a middle-aged star. So the magnetic field in a young star is so strong that, to the best of our understanding, it actually truncates the disk. Because when the disk gets in close to the star, the central, the part of the disk that's closest to the star heats up. And so it ionizes. And once you have charged particles, the charged particles can, quote, see the magnetic field. And so that means that the charged matter, is funneled along the field lines and then crashes down onto the star. And much like, water from a faucet crashing into a sink, that matter crashes onto the star and it makes a shock where it hits. So you can get a hot spot. So the star spots are cold, but the shock is hot. And so you end up with rings or spots from accretion that are where that accreting matter hits the star. And so you get blue light and ultraviolet light from that shock. You don't generally get X-rays. The X-rays, usually you need non-thermal emission. So you have flares that do that. And the circumstellar disk is dusty. And because it's intercepting a fraction of the star's light, you end up heating up the disk. And so it glows in the infrared. So the closer you get to the star, the warmer it is. And so the shorter the wavelength of IR, that is important. Because disks are probably flared, you probably get scattered light, because the disk that's here, that's really close to, if it was exactly flat, then the disk that's right here can't really see the star. But as soon as the disk starts to flare, that part now sees, it intercepts more light from the star than the part right there does. There's all sorts of fantastic chemistry that you have to worry about to do this right, because the center of the disk is colder. The middle of the disk, like the center, like the part that's not heated, is colder than the stuff that's on the surface. And the disk itself may generate magnetic fields and have its own flares. And some of the big flares that happen on the star may be connected to the disk. It's really complicated. It's really cool, but it's really complicated. So that's where all of the light is coming from. X-rays from the flares, UV from the shock. I guess I didn't explicitly mention that you get H-alpha emission lines from the flares, but also from the accretion columns. And then you get infrared from the disk. And you can get optical scattered light from the disk as well. All of this varies on pretty much any time scale anybody has had a chance to look. So this is data from HST of a nearly edge-on disk. And you can see that there's a jet coming off this star. And you can see the disk is flared. And if you look closely, you can see there's a bright part of the disk. That's probably because there's an accretion spot that's rotating on that star, and we're getting scattered light from that hot spot off the flare of the disk. This is a movie of, in the infrared, of, it turns out probably what's going on is that is an edge-on disk for a binary. And probably what's going on is that the binary is orbiting in a highly elliptical orbit. So you get a brightening when the stars are close together, and then it fades as the stars move apart, and then bright as it's close together and fades as it moves apart. And you can see that light, that pulse, is moving out through the cloud. So lots of variability. Again, to break up into teams to talk about this plot. Here's the important bits. So the earliest phase is called class 0. Sometimes it's called stage 0. This is the part where the young star is probably accreting most of its mass. The central mass is relatively small. The envelope still has an awful lot of mass that will eventually become part of the star. The spectral energy distribution is basically just the cocoon, right? It's the intercepted, the cocoon has intercepted pretty much all the light from the central object, and so it's reprocessing it and emitting it as a cold black body. Class 1 is a little bit older. You still have somewhat of an envelope, but you have a disk. The reason you have a disk is because of conservation of angular momentum. It can't fall just radially in. Every cloud probably has at least a little bit of spin, and so in order to conserve angular momentum, the stuff has to fall into a disk before it falls into the star. So you still have an envelope somewhat, but you have a pretty big disk still too. Here you can see the central source is bigger, the envelope is much smaller, and you're getting some contribution in terms of the SED that you observe on the right. You're seeing some contribution from the central object, but most of the energy is still the infrared that's reprocessed by the dust. Then a little bit older, the envelope is gone. You still have a big disk, though. Those are class 2s. And the SED shows you that most of the energy is actually coming from the central object now, but you still have a substantial infrared excess from the big disk that's still there. Then eventually the disk thins out, and you get planets from the disk. And then the SED that you see is mostly just a black body. There might be a little bit of an infrared excess depending on how much dust is left in the disk. This is an entirely empirical description. It's based entirely on the SED shape. The interpretation is a separate step. And class 0 are sometimes called protostars. There's a flat class in between, sometimes between class 2 and class 1, because class 1, the SED is sloped up, and class 2, the SED is sloped down. So there has to be a transition where they're flat. And so some people like having a flat class in between. Class 2s are sometimes called CTTSs or classical T-Tauri. Weak-lined T-Tauri are the older versions. So that just means that they are, there's some characteristics they have in common, but their emission lines are weaker, hence weak-line T-Tauri. Transition disks are probably those guys that are in between class 2s and class 3s. And then debris disks, you can get a second generation of dust, because once you start forming planetesimals in the disk, they do sometimes hit each other. And so you can end up with a second generation of dust, which is likely to be the source of debris disk dust. So this process strictly only applies to low mass stars. High mass stars probably do this just faster. We don't know yet, because it's harder there's fewer high mass stars and they evolve faster, so it's harder to catch them in the act. Class 0s are the shortest lived, and they're the hardest to catch. Not too long ago, the list of all the class 0s that we knew could fit on far less than one page of a journal article. Spitzer revolutionized that. There's now lots of class 0s and lots of class 1s. Class 0s used to be defined simply as undetectable in the infrared. Even before Spitzer, that was not a very good definition. But the classification really is based on the SED, and we're going to be making SEDs, and we're going to put them in classification bins to see how many we get. Most of the ones that we find are probably going to be class 2, I would guess. The physical interpretation of that SED is degree of embeddedness. In other words, the class 0s are still buried deep, and the class 3s have freed themselves from their cocoon. But that next step, that interpretation from SED to degree of embeddedness, is one logical step. And then degree of embeddedness to age is another separate logical step. There's plenty of confusion, right, where you have lots of clusters of stars that seem to be the same age, and you've got a bunch of CTTSs and a bunch of WTTSs. I personally have found things where we had a prestellar clump, a class 0, a class 1, and a class 2 all within such a small area that the only way they could be there all together in a small area is that they were all the same age, and yet they were hugely different in terms of their SED shape. So that interpretation of embeddedness to age is a separate logical step. Nomenclature really is a nightmare. We're going to just call all of these things young stellar objects or YSOs. You will see other names for various stages. You just have to be clear when you're writing in a poster or in a talk or in a journal article for sure. You have to be very clear about what you mean when you use these words. Like I said, class 2s are also called classical T-Tauri, and class 3s are weak-lined T-Tauri. And then flat got stuck in the middle, and debris disks are second generation dust. Class 2s, like I said, class 2s and 3s are found at the same ages. So some stars lose their disks very quickly and some don't. We don't know why. As far as we can tell, class 0s and 1s are found at the same age, which is really strange. It's very hard to figure out what's going on. And part of why we may be fooled with this is that imagine if we had here a class 3 star. So we have a star with a little bit of a dust disk. And we're going to rotate it so that it's edge on. And now we're looking at the star through the disk. We might be fooled into thinking it's a class 2. So the inclination might matter. Some things we think are the youngest protostars may be just edge on older things. We don't know yet. We're trying to figure that out. Most people, when they talk about class 0, 1, flat 2, and 3, they mean a series going from youngest to oldest. But it's important to remember that that is an assumption, and there's a lot of uncertainties in that. Chances are, I think we're going to find mostly class 2s, but that's just a guess. Class 2 is the longest lived stage of stars that still have an infrared excess, and we're going to be using some optical stuff, and we're not going to be using primarily infrared, but I'm thinking that we're still going to be finding mostly class 2s. The 2015 team YSOs, the ones that they reported on, were 11% class 1, 24% flat, 43% class 2, and 21% class 3s. So when you combine theirs plus the ones that have been published in the literature since then, I have 21% class 1s, 12% flats, 32% 2s, and 34% 3s. Many of our targets may not have much data. They may not have data past 5 microns. And that's really hard because that SED slope is defined between 2 and 25 microns. So if all we have is between 2 and 5 microns, that's a really short level arm. So slope may not be terribly meaningful for a lot of the sources that we find. And I've shown you this movie several times before. One of the things I'll ask you when we do this live and in person is to get together and brainstorm about what you know about this movie. Those are some of the things that I noticed, that the overall brightness increases. The shape doesn't change, but the brightness increases as the temperature increases, and the peak moves bluer as the temperature increases. UV and optical filters are generally on the Veen side of the curve. Optical and near-IR filters are generally covering the peak. So optical and some near-IR colors can be mapped directly to the temperature of the star. Near-infrared and Spitzer's mid-infrared filters and WISE's mid-infrared filters are on the Rayleigh-Jeans side of the curve. That Rayleigh-Jeans slope does not change through all of these temperatures, and so the IR colors are 0 for normal stars and non-zero for things that don't have this SED shape. If all you have is points on the Rayleigh-Jeans side, you can learn some things about the source, but you really are helped a lot when you have Veen side data. And when Spitzer was new, a lot of times we didn't have any optical data. But we in this project have a lot of optical data, so that's going to really help us understand what the complete SED shape is. And I haven't talked about reddening yet. But now we're going to do that. What about reddening? So I'm going to break you up into teams and brainstorm about what you know about this movie. Things that I noticed, stars are getting reddened by dust grains in the ISM just like sunsets get red. The movie is a 6,000 Kelvin black body with varying extinctions. Just like sunsets, the blue is affected more than the red. The blue side gets pulled down really fast, and it's not the same shape as it gets pulled down as it was before. You have to have a pretty high extinction before you notice any effects in the mid-infrared. The deep absorption that shows up at 10 micron is not a hole in the disk. It is a broad silicate absorption line. And if all you have is photometry, you can be fooled because you can't tell if the object you're looking at is a low mass star or a high mass star with lots of extinction. And that's part of why we have to be careful about only referring to our new YSOs as YSO candidates, because until we get spectroscopy, we don't know for a fact. And even if we get spectroscopy, we still might not know for a fact that they're young. So the important thing is that reddening is going to change the positions of objects in the color magnitude diagrams because it's going to change the shape of the observed SED.